Today we'll talk about the diesel engine and the diesel cycle. The way that combustion is initiated in the diesel engine is very different from a gas engine. In a gas engine, you have a spark plug which provides a spark to initiate the combustion. However, in a diesel engine, you do not have a spark plug. So what happens is called compression ignition. So how does that work? Let's take a look. We still have the four strokes: power stroke, exhaust stroke, intake stroke, and the compression stroke. Let's start from the intake stroke. The intake stroke takes in air only, unlike a gas engine that takes in the mixture of air and fuel. So during the intake stroke, the piston moves down and sucks in air only. And then we move on to the next stroke, which is the compression stroke. Piston moves up and compresses the air. What's going to happen is the temperature and the pressure of the air will go up. And then we move on to the power stroke. What happens is here we directly inject the fuel into the hot air. We do not have a spark anymore. Instead, we directly inject the fuel into the hot air, and then combustion will happen automatically because diesel is more active than gas, so it doesn't require a spark. And then after combustion completes, what's going to happen is you will have an expansion process within the power stroke, pushing down the piston. After the piston is pushed down to the bottom, we move on to the next stroke, which is exhaust stroke. The piston now will move up to push out the hot exhaust, and then goes back to the intake stroke to suck in the new cold air. So that's the four strokes. And then we do the same thing. We convert the four strokes into the thermodynamic processes. What we do first is to, same as before, combine the exhaust and intake strokes into one single step. In reality, what happens is you push out the hot exhaust and then you suck in the new cold air. But in thermodynamics, we assume the hot exhaust will just sit inside the cylinder and then it will lose heat to cool down and become the new cold air. So in thermodynamics, this is a closed system. There's no mass transfer. And exhaust plus intake strokes are converted into one single step. That is the heat loss process at constant volume. And then we move on to the compression stroke. Compression stroke is still the same. It is isentropic compression. And then we move on to the next one, the power stroke. The power stroke has two steps. The first step is combustion. We call combustion process 421. And in this time, combustion process is modeled as, again, an heat addition process. However, not at constant volume anymore, but at constant pressure. Why is it not at constant volume anymore? Before, when you have a gas engine, combustion process is modeled as a heat addition process at constant volume. Why? Because before we have a spark, and if you provide a spark, combustion happens really, really fast, leaving no time for the piston to move. So volume must be constant. However, when we move on to diesel engine, we do not have a spark. The combustion happens automatically, so it's not as fast as when you have a spark. So the piston will have time during this combustion process to move down. That's why volume is no longer constant, but pressure is constant. That's process 421, how we model the combustion process. And after the combustion process, it's the expansion process, pushing down the piston, and that is still the same as before. That's isentropic expansion, 122. And then exhaust plus intake, like we said before, are combined into one step, that is heat loss at constant volume. And then compression process, same as before, is isentropic compression, 3 to 4. And one very important thing here is we want to talk about the whole cycle is modeled as a closed system rather than a control volume. So whenever you use first law, make sure you choose the short one, not the long one. Okay, so now we do the same thing. We go back to our notes and we will sketch the 4 steps on the 2 diagrams, P versus nu and a T versus S diagram. Oh, again, you see air standard diesel cycle. If you see the word air standard, what does that mean? That means you can assume the gas inside the cylinder is air, while in fact it's a mixture of many different gases. If it is air standard, that means you can just use air properties for the gas inside the cylinder. Okay, let's go back to the diagrams. First, we have P versus nu diagram. And second one is T versus S diagram. Just like before, we do not need to sketch the vapor dome anymore because everything is superheated here. So everything is to the right side of the vapor dome. There's no need for us to sketch the vapor dome anymore. Let's start from process 421. 421 is still the same, it's the combustion process. And we model the combustion process as a heat addition process, this time at constant pressure. It's not constant volume anymore. And then after the combustion process, what you will have is the expansion. The gas will expand and push down the piston. We call it isentropic expansion. And then those 2 steps combined together is the power stroke. Okay, after 1 to 2, we have 2 to 3. 2 to 3 is the combined exhaust and intake strokes. We combine those 2 strokes into one single step, that is 2 to 3. And what is 2 to 3? It is a heat loss process at constant volume. And then 3 to 4, same as before, that is the compression stroke. And we call it isentropic compression. So now let's start from 4 to 1 on the P versus nu diagram. 4 to 1 is a heat addition process at constant pressure. Constant pressure, and the pressure is my y coordinate. If my y coordinate is constant, then that must be a horizontal line. Okay, to what direction? To the right or to the left? We need to check the x coordinate, which is specific volume. How does specific volume change during the combustion process? We said the combustion process is not as quick as in the gas engine. The piston will have time to move down. The piston will be pushed down a little bit, so the volume will actually becomes bigger. If volume becomes bigger, then specific volume nu must become bigger. So that's why 4 to 1 must be horizontal and to the right, since volume becomes bigger. Okay, and then we sketch 1 to 2. How do we sketch 1 to 2? 1 to 2 is an expansion process, so specific volume nu, which is the x coordinate, becomes bigger. So 1 to 2 to the right. It's also because of this, also because it is an expansion process, pressure becomes smaller, so you must go down. That's why 1 to 2 must go down and to the right. Slightly curved. and give it a subscript. Because it is isentropic, entropy must be constant. And then let's sketch 223. 223 is a heat loss process at constant volume. It is at constant volume, so my x-coordinate doesn't change. 223 must be vertical, up or down. Since it is a heat loss process, you lose energy, so pressure, which is the y-coordinate, must become smaller. So 223 vertical and go down. And then finally 324. 324 is isentropic compression. Because it is a compression process, volume becomes smaller, so x-coordinate becomes smaller. We need to move to the left. And then up or down. Since it is a compression process, pressure must go up. So 324 to the left and up. So we connect 324 with a curve. And just the same as before, add a note, entropy is constant since it is isentropic. And then we sketch everything again on a T versus S diagram. Let's start from 4 to 1. 4 to 1 is a heat addition process at constant pressure. Heat addition. If you gain heat, you also gain entropy, so the x-coordinate, which is entropy, becomes bigger, so 4 to 1 to the right. Up or down. Heat addition, so temperature must go up, so to the right and go up. 4 to 1 to the right and go up. And make a note, pressure is constant. Okay, next one, 1 to 2. 1 to 2 is an isentropic expansion. If it is isentropic, it must be vertical, up or down. It's an expansion process, so temperature must go down. So 1 to 2 must be vertical and going down. Next one, 2 to 3. 2 to 3 is a heat loss process at constant volume. Heat loss. If you lose heat, you also lose entropy, and entropy is your x-coordinate, so your x-coordinate is becoming smaller to the left. Up or down. Heat loss. If you lose heat, temperature must become smaller, so to the left and go down. And make a note here. For 2 to 3, volume is constant. Nu equal to constant. And then last one, 3 to 4. 3 to 4 is isentropic compression. Isentropic, so it must be vertical. Up or down. Since it is a compression process, temperature, which is the y-coordinate, must be going up. So 3 to 4 must be vertical and go up. Okay, so this is how you sketch the diagram. And then just like before, doesn't matter which diagram you look at, the area of the enclosure tells you the same thing. Area of the enclosure is equal to W cycle per unit mass on either diagram. Doesn't matter which one. P versus nu or T versus S, the area of the enclosure tells you the same thing, that is W cycle per unit mass. Okay, so now we do some analysis about each step. Let's start from 4 to 1. 4 to 1 is heat addition at constant pressure. We will look for work and heat transfer of each single step. We start from process 4 to 1. How do we look for work? W 4 to 1 is equal to integral P dV. Lower limit is V4, upper limit is V1. Okay, since this process is at constant pressure, so the integrand P is constant. So I can take P out of it. You can call it either P1 or P4 because they are equal. And then what is left is V1 minus V4. And then final solution is we divide both left-hand side and right-hand side by mass. So right-hand side becomes P4 times nu1 minus nu4. This is work for process 421. And then next one, we look for heat transfer. We have work, we're looking for heat transfer. We have to use first law. And remember, this is a closed system, so we have to use the short version. Q421 minus W421 equal to delta E 421. Delta E has three components. They are delta KE, delta PE, and delta U. Okay, and just like before, you can neglect delta KE and delta PE. So Q421 is equal to W421 plus delta U. And then we divide every term by mass. Q421 over mass equal to W421 over mass plus delta lowercase u 421. And then W421 per unit mass. Delta means change, final minus initial, U1 minus U4. And we do have an expression of W421, which is here. And then what we can do is to plug in. So our new solution for Q421 per unit mass is P4 nu 1 minus P4 nu 4 plus U1 minus U4. And then we rearrange this equation. It becomes U1 plus P4 nu 1 minus U4 plus P4 nu 4. And then let's recall P4 is actually equal to P1 since this is a constant pressure process. So this equation becomes U1 plus P1 nu 1 minus U4 plus P4 nu 4. And again, recall what is U plus P nu? That is the definition of specific enthalpy, lowercase h. So now this equation just becomes H1 minus H4. So now to summarize our conclusion, W421 per unit mass is equal to P4 times nu1 minus nu4. And heat transfer Q421 per unit mass is equal to H1 minus H4. That's process 421, combustion. And then let's move on to the next one, 122. Process 122 is isentropic expansion. And which one's easier? Heat transfer must be easier. Heat transfer is zero. Why? Because the process is isentropic. And isentropic means there's no heat transfer and the process is reversible. And now we have heat transfer. We're looking for work. Use first law, the short one. And the solution is W122 over mass equal to U1 minus U2. And then we do the same thing for process 223. Process 223 is heat loss at constant volume. Which one is easier? Work must be easier. Work must be equal to 0. Why? Because work is equal to integral PDV. What is derivative volume for this process? Volume is constant, so derivative of a constant must be 0. That's why there's no work. And then we use first law, again, to look for heat transfer. The solution is U2 minus U3. And then the last step is process 324. And that is isentropic compression. And again, which one is easier? Heat transfer. Heat transfer must be equal to 0 because it is isentropic. And then we use first law to look for work. Solution is U4 minus U3. Okay, so that's every single step. And then again, we have compression ratio. Compression ratio. Still, it's gamma. And the definition of compression ratio is still the same. The biggest volume in the process divided by the smallest volume in the process. Let's go to the diagram, P versus nu. Take a look. Which point has the highest volume? Or in other words, which point has the highest x-coordinate? It's point 2 or point 3. V2 equal to V3 since it's vertical line. And which point has the smallest volume? Or in other words, which point has the smallest x-coordinate? Number 4. Okay, so this equation becomes V3 over V4. And keep in mind, V3 is equal to V2. And then something new. Cutoff ratio. This is something new for diesel cycle. We call it gamma C. And the definition is very straightforward. It's V1 over V4. Okay, what is V1 over V4? 4 to 1 is the combustion process. And we know for a diesel engine, the combustion process is not at constant volume. So V1 is not equal to V4. That's why this value is not equal to 1. However, if you have a gas engine, 4 to 1, the combustion process is at constant volume. So that's why gamma C, cutoff ratio for a gas engine must be equal to 1. That's also the reason why we did not talk about cutoff ratio when we were talking about a gas engine, because for gas engine this value is equal to 1, and for diesel engine this value is not equal to 1. Okay, and again, same as before, if the process is isentropic and also ideal gas, you can use the following equations. What processes are isentropic? They are 1 to 2 and 3 to 4. So for 1 to 2, we have this equation. And then 3 to 4 is also isentropic. And again, what is K? K is still the ratio of the two specific heats. The value of K is equal to 1.4 if the substance is air. And again, efficiency has an equation 1 minus 1 over gamma K minus 1. Okay, so now let's talk about how does gamma affect on efficiency. For a gas engine, we know if the compression ratio gamma is high, you will end up with a high efficiency. Is that still true for a diesel engine? Let's take a look. If gamma goes up, the denominator will become big, so the whole second term will become small. 1 minus something small, your solution will go up. So if gamma goes up, your efficiency eta goes up. Same as before. The higher the compression ratio is, the higher your efficiency will be. The reason why usually a diesel engine is more efficient than a gas engine is because diesel engine usually has a higher compression ratio gamma compared to a gas engine.